Uh, does anyone, Professor, your mic sounds a little messed up. Is anyone else hearing that?
Yeah, nobody, everybody hears like a squeak.
Better?
Yeah.
Yeah, it's much better.
Yeah, it's that same issue from the other class. Usually it doesn't do it when I switch to my laptop, but that's what happened. Okay, so last time we were finishing up on instantaneous velocity and how we calculated it through the derivative of the position function. Right, we were doing over here. If there's a rocket moving along in this path, the position is given by this. The velocity, the instantaneous velocity at any point is given by the derivative. And then the acceleration is just the derivative of the velocity, right? It's the change in the velocity. And so it's like a nested thing. You go back and forth between each one of these, either through an integral. So, no. That marker's not working. It's unfortunate. You know, you integrate. Right, to go this way, and then you take the derivative to go this way. I'm just going to write this to go this way, right? And let's finish this problem. Let's do it from the beginning. So there's two types of velocities, right? The average velocity and then the instantaneous velocity that we calculated. And so in this problem, I showed you the instantaneous velocity, but actually, if we do it from the beginning, I'll read off the problem. If you want to join along in your books, it's example 2.3. So a jet engine moves along an experimental track. Over here, it's at 20 meters, roughly 20 meters, and this is x1. And over here is x2, and that's equal, and this lies in between 50 and 60. And this is actually, right? Now, for part A, it actually determined the displacement of the engine during the time interval T1 to T2. And T1 over here is 2 seconds or 3 seconds. And T2 is 5 seconds. Now,
Professor, which page number is that?
24 in the book. I don't know in the PDF if you're using a PDF version. What's 24? Section, the last part of section 2.3. It's this one. All right, so, and then the equation of motion is given to us, but the position function is given to us, and it's a squared plus b. A is equal to 2.1 meters squared. B is equal to 2.8 meters. So it starts off at 2.8 meters, right? And it's important to note here, right? This rocket, right? It's a certain size. So what do we mean by it starts off at that it's at this position, right? Which part of this rocket is at this position, right? so when we talk about the position of a car, right? Which part do we take as the position that we mark as the position, right? If the car's going a long distance, it doesn't matter, right? If the car's traveling from here to California, the size of the car is extremely small, right? It's a very low percentage, right? So at that point, we take the car to be a point particle is what we say. It's just an infinitesimally small point that we track along, right? Here, when the distance is comparable to the object, what we normally use as the point is what we call the center of mass, and this we'll get into later on. But so if we take all the mass and we crumple it down and we average the position of all the mass to one point, that's the center of mass. So usually, for now, we'll just call the center of mass at the center of whatever object we're looking at. Later on, if the different densities, it could be different from the center of this of the shape itself. So, but for now, we'll track the center of the object. And it really doesn't matter, right? Just like how you choose your origin or the time that you start, it doesn't actually matter. As long as you stay consistent throughout the problem, you should be okay. You choose it to be convenient. And it's just convenient to pick the center as the point that we follow along. So if you notice that with this equation, at time 0, when we start the rocket, right, that's when we take out time 0, since we could choose anything to be 0, but we choose what's the most convenient. So when we start the rocket, and when it actually starts, the instant it starts moving, we'll take that to be 0, because it's just the most convenient. Otherwise, you need to add a factor to account for this wait time or whatnot. So at 0, it starts at 2.10 meters, right? So we could take that to be maybe the fact that the rocket is some length, right? All right, so the first part of the question, A, is what is its displacement? And what's the formula for displacement? Somebody wants to shout it out or write it down. Delta x is what we usually call as the displacement.
Velocity multiplied by time.
So forget that we can figure out velocity. We're just given position function. All right, so this position function will tell us where we're at each point. So displacement going from 3 to 5 seconds. Right. So all it is where we take where we finish at and we subtract where we start at, right? We subtract from the origin. So it would be x2, this position, minus x1, right? Now, we're not explicitly given the coordinates, we have to calculate it. So this is equal to, x2 is equal to x at time 5. So when we plug 5 into this function, that's what we'll get, minus the position when it starts at, which is 3. And now we plug it in. So I'm not going to plug in these numbers. I'm just going to write A. A and B are just constants, and the only thing that changes is time, right? These are just constants that we just, so just think of these as just numbers, right? And it's just easier to write one letter than 3 numbers. So A 5 squared plus b minus a 3 squared plus b. And this is all in parentheses because we minus it. And if you look, the b's cancel out. And we're left with a times 5 squared minus 3 squared. A can be pulled outside because it's multiplied by both. And a little convenient thing, 5 squared minus 3 squared, or 25 minus 9 is 16, or it's 4 squared. So this is equal to 4 squared. This is a little convenient thing that people use in construction because they don't have to actually calculate the squares. They can measure the legs of the triangle and then they can determine if something's square from this. So the fact that this works out like this, it's used all the time in everyday practical life. And then we could finish the calculations. I'll just plug in the number and it'll come out to 33.6 meters, right? And then it's important to do, let's do a dimensional analysis right below it, right? It's important to keep it into account the units, right? A is meters. I'll put it right below. Can you guys see that? Fine. Oh, yes, I'm recording, great. Okay, so so A is meters per second squared, and then we have seconds squared over here, that's multiplied. So the seconds squared cancel out, and we're left with meters. So the units work out. All right. Any questions on this part? Okay. Next, part B. I should have left that. I like this in different color. So part B is they ask you for what is the average velocity? What is the average velocity during this time? From 3 to 5. How do we calculate the average velocity? Anybody?
That change in x over change in t?
Yes. So we just take the two endpoints and we calculate how far it moved per unit of time between these two points. We don't care about if the velocity changed in between. We care about the average velocity during this time. So we just care about the displacement in a given amount of time, right? So average velocity is equal to the displacement divided by the time elapsed. So here, if you remember, the displacement is given by this. This is for A. That's the answer for A. So we just use that. And we get 33.6 over 5 minus 3, which is just 2. And when we divide that, we get 16.5 8. And then it works out, right? Because this is meters, and then both of these quantities are seconds. I'll try to put these brackets around the units as much as possible. So it works out, right? Meters per second. How many meters you travel in 1 second? Or for each second, right? So this works out. So then we have B equals and then part C it asks you for the instantaneous velocity. The velocity. We'll just label it like that. What is the velocity? And can anybody tell me how to calculate the velocity from this? So what do we want to take?
Is that at a certain point?
No. Well, hold on. Let me see if they. Okay. Yes. Determine the instantaneous velocity at 5 seconds when it ends. So how would we go about doing this? What is
Find
it?
the
Yes.
derivative of x of and then just plug in 5.
Exactly. So it's the derivative of the position function. Now, as a little reminder, what the derivative is, so there's an appendix in the book, appendix 2, and they give you, they tell you how to do each derivatives, but the different derivatives. But for this type of function, where we just have the variable t as a power to some power, this type of derivative, in case you forgot, in general, is this, right? So C is a constant here. This is on page 23. And T is the variable in this case. We're taking the derivative with respect to T. And then it's to some n power. And then what we do here is we bring down the n and we multiply it by the function. We leave C alone, and then we subtract 1 from the exponent. Take one of these n's down, we subtract 1, right? And then it should be noted that if you follow this to the last step, where n is 0, we'll get this, right, where we're just taking the derivative of C, and this is equal to 0. So the derivative of a constant is 0. It's just any number. So let's do this derivative. So if we take this derivative, let's look at it. So for the first part, we take down the 2. So 2 times a, which is the constant, and then we subtract 1 from the 2, which gives us 1. So it's t. When we take the derivative over here, it's 0, because this b is just a constant. So the instantaneous velocity is given by this. And then I should put this as a function of t. And then since the x is for 5, and then so then v5 is just equal to 2 times a times t, which is solution is 21 meters per second at 5. So this is part C. This is B. All right. And that's it for this problem. Okay. Any questions so far? Move on. Hold on, guys. All right. Now, I introduced last time acceleration. I'm going to erase these results. And let me just write the instantaneous velocity down here. So this is the instantaneous velocity. We got the position. And to fully describe the motion of this, we kind of need to know the acceleration. Now, what is the acceleration? The instantaneous acceleration, let's say. All right, so why don't we do the average acceleration? So so applying what you learned about the velocity, how velocity relates to position, it's the same way that acceleration works to velocity. So we want to calculate the average velocity. What do you expect to do? Anybody?
Sorry.
Exactly. It's the change. It's the change of velocity over time. So it's instead of delta x over delta t, now we have delta v over delta t. How much does the velocity change in a given amount of time? So for this position, for these two times, let's calculate the acceleration, the average acceleration. So we have v2 minus v1, right? Because we have to subtract the initial velocity for that time. Hold on, guys. I'll be right back. Sorry, guys. My daughter's playing with this cat app, and you just hear this like kitten crying. Really annoying. But anyway, so we have this. So let's calculate the velocity for each time. So this is a over 2 at 3, or I'm sorry, at 5 minus a over 2 at 3. And then we have this, right? Let me just erase this. Put this. Now, we'll see what happens. So we can pull out the A's from both of these. Right. So then in the end, the acceleration, let me erase this. The acceleration is equal to just 2a. You guys see that? So actually in this problem, and we'll show it in a second, the time does not really matter, right? You can see it. It cancels itself out. And this is what we call constant acceleration, right? We'll get into it when we do forces, but it implies a constant force, and there's a constant acceleration. The acceleration doesn't change over time, right? And these are generally the problems that we'll be dealing with in kinematics. There are constant acceleration problems. So now this is the average acceleration during this time. So what's the instantaneous acceleration? How do we calculate that?
Second derivative.
That's right. It's the second derivative of the position. So, and then let's figure out what it is at 5 seconds. Since we did it for we calculated the velocity at 5 seconds, right? So, and this is actually example 2.7. If you want to follow along in the book, this is example 2.7. So let's calculate what AT is, right? It's just the derivative of the velocity function, right? Or we could write it as the derivative of the derivative of the position of the position. Right? And usually we'll use we call this as the second derivative, and it would be given like this. And these superscripts over here, this tells you to do it that many times, right? So you just take the derivative with respect to t of the variable down here twice, right? And we already calculated the first derivative. This is the first derivative. So we don't need to do this twice again. So let's just calculate the derivative of 2a t. And this is, not surprisingly, equal to just 2a, right? Because following this rule, n is 1, so we can leave it out. And then t goes to 0. The exponent over here goes to 0. So t is 1. The t to the 0, or anything to the 0 power is just 1. So we're left with 2a, right? And this agrees with what we found with the average velocity. When we calculated the average velocity, we could pull out all the time, right? We were able to pull it out, right? The average velocity ended up looking something like this. Right? And it ended up that the time didn't matter. So, and this shows it, proves it. Right? So it all agrees. And if you look at the units of acceleration are meters over second squared. And these are the units for acceleration. Is it easy to see the board if I dim the lights?
Yes.
Like that? Is that easier or harder?
A little easier.
All right, great. But you guys can read the board just fine? When
You have to write a little bit bigger for some of them, I think. But mostly, yeah. But like for X1, for example, I can't really see that at all.
Okay. I'll use darker colors. I'll try to stay away from red. The thing is that, you know, this board is not the biggest, so
yeah.
So it's difficult, and you need to keep all the information up. All right, so we calculated all the different parameters. We have the velocity, the acceleration, and everything else. So let's actually study what this looks like. All right. So let me transpose this, right? So imagine instead of the rocket going sideways, it's going up, right? So let's see what this looks like over time, right? So let's say, at T1, that's much better, right? Now you guys can see it very clearly.
Yeah,
Alright.
very clear. Very clear.
Right. This is S, and then this is X, right? And we're going upwards, right? So at T1, let's say if we choose T1, we have our rocket, it's over here. At T2, it flies up a little bit higher. And then you got to realize it's under a constant acceleration. So if these are equally spaced, let's say they are 2, 4, 6. So then at 6 seconds, it will, between 4 and 6, it will travel roughly 4 times faster. Just roughly. We would have to actually calculate the average, but just for time's sake, don't worry about it. Right? And then at 8 seconds, it's even picked up even more speed. So then it travels 4 times, almost 4 times as fast. And let's draw a graph through the midpoint that we're using to track the rocket. And if you notice, what happens is that you get this curved function as it increases, right? Because between each time interval, it's going faster and faster, so it's traveling further distance at each time interval. So you guys can see it. Let me redraw it so that without the rockets at each point. So if we take the position, it'll look something like this, right? Now the velocity, instantaneous velocity, like I went over last time, is, I'm going to use red just to accentuate it. The instantaneous velocity is the tangent. So this represents, the slope at this point represents the instantaneous velocity. And the acceleration in this curve is actually given by how curved the surface is. This is what the second derivative tells us. How much does this curve, right? Because if there's no acceleration, let's just say we had some constant velocity, it would only be a straight line, right? Because for each time interval, you only increase in the same amount, so you're just going up at a steady rate.